Welcome back. We're coming to the close of the semester here, so we only got a couple more sections to go. So we're going to go through 10.8, and that'll be the end of where we're going to get to. So this is 10.6, the alternating series test. Thankfully, it's one of the easier tests to carry out. However, there are a couple of concepts in this section that we'll want to take a little bit of a careful look at, just because some weird things can happen in a couple of cases. Okay, so we've had a whole bunch of tests thus far. You had the integral test, comparison, both direct and limit comparison, had geometric series, and we had root and ratio tests. So all of those either assumed that we had positive terms to begin with, or they took the absolute value to make everything positive. So they don't really count the fact that some things are positive, some things are negative, because they take absolute values all the time. The alternating series test actually builds in this fact. So let's take an example here. I'm taking the sum n equals 1 to infinity. Negative 1 to the n plus 1. Whenever you see negative 1 to a power like that, it just means it's flipping signs back and forth, positive, negative, positive, negative. If it's an n rather than an n plus 1, it'll start with the negative. In this case, since n plus 1, it's going to start with negative 1 squared, so it'll start positive. So that's called an alternating series. Every other term is positive. Okay, so if we were to write that one out, we'd get 1 minus a half plus a third minus a fourth plus a fifth, and so on. Now, if we take a look at the partial sums, okay, s sub 1 is just the first term. S sub 2 is 1 minus a half, which is 0.5. S sub 3 is 1 minus a half plus a third, and that turns out to be 0.833 repeating. Then if we subtract the quarter, you get 0.5833. And if we keep going, that should be the fifth here. I don't know why I had mislabeled there. S sub 5 is 0.7833. And then S sub 6 is 0.61666 repeating. And that could keep on going. Notice each time you go down, we went down by a half, but only back up by a third. So each time we trade directions, we're not going as far in this one. So we went down a half, up a third, down a quarter, up a fifth, down a sixth. So each time it's moving back and forth, it's doing so by less. And you'll notice these partial sums that are odd are going down. These partial sums that are even are going up. Eventually, they're going to meet. And so this thing's going to converge. But it's converging because of that back and forth action going on. So this leads us to what's called the alternating series test. So a lot of notation in this one. So we assume that the term can be written as negative 1 to the n times u sub n. Okay, so we pull out the negative 1 power. And notice, I do note here, it could be negative 1 to the n plus 1. That's just starting with a positive rather than starting with a negative. Now, these u's, I have to be positive. So notice the terms are flipping back and forth, but the u's are positive. So the terms are actually going positive, negative. And the terms are shrinking in size. Okay, so in this case, the u sub 1 is 1, u sub 2 is half, u sub 3 is a third, u sub 4 is a fourth, and so on. It's just the positive part. And then you got this negative 1 that's alternating. They are shrinking in size. Now, this has to be true after some point. So it might be a case that the first two terms don't fit it. But at some point in time, the terms have to be shrinking. Then we get something that we've wanted to do from the beginning, but we're never really allowed to do. Then we can just use the nth term. Okay. Very early on, we talked about the nth term had to go to 0, but that didn't prove convergence. But in the alternating series with these conditions, it does. So in this case, now notice you have to have all of these things satisfied. If the terms go to 0, then the sum converges. Okay, so it's one of those, it's actually not a hard test to carry out. The main thing to realize, it only applies in some very restricted settings. You have to have something that's going back and forth, positive and negative. The size of the terms has to be going to 0, and it has to be going down steadily. Okay, so it can't pop back up and keep coming back down. I mean, it can do that for like 2 or 3 terms, but it has to eventually go to the point where it's monotone decreasing. Okay, now one interesting thing here, if we tried any of our other tests, because they took absolute value, the sum of just 1 over n, that diverged. That was a p-series of p equals 1. So this test is the first one that uses the fact that some of the terms are negative. Notice we can use any of the other tests using absolute values to show convergence. And one fact you can use, that if the sum of the absolute values converges, in other words, to get rid of all the negative signs, and that sum converges, then the sum with any negative signs will also converge. Okay, so when it's a series alternating, we can use either the alternating series test or any of the other tests we've used before to try and show convergence. Showing divergence is a little tricky part, because unfortunately this is not an if and only if. So if this sum diverges, the alternating series test could still make the sum without the absolute values converge, as we had here, because we know that the sum n equals 1 to infinity of just 1 over n with no alternating, that is infinite. Okay, it's a p-series. Okay, so p-series of p equals 1, and we know that p has to be greater than 1 for it to converge. Okay, so this is a handy one. It basically says when you have something alternating, you can use the alternating series test or any of the others. Now, when that happens, so when you use this part, so when you use one of the other tests other than alternating series test, we say that the sum here converges absolutely. Okay, so for example, we have negative 1 to the n over n squared. Well, that would be negative 1 over 1 squared plus 1 over 2 squared minus 1 over 3 squared plus 1 over 4 squared. And so we notice that this is alternating. The u sub n's are 1 over n squared, and those most certainly, make that a little bigger there. The u sub n's are 1 over n squared. They're shrinking. Okay, so by alternating series test, we know this converges. But note, the sum 1 over n squared without the alternating part also converges. And in this case, we would say that this first one, not only does it converge, we would say it converges absolutely, because even if I get rid of that negative sign, it still converges. Okay, if we have the case that the sum n equals 1 to infinity of a sub n converges, and the sum n equals 1 to infinity of absolute value of a sub n diverges, which was the case with our first example. Okay, remember back here, we had this one converging, but without that negative 1, it diverged. Then we say that this sum, n equals 1 to infinity of a sub n, converges conditionally. Now, basically what it means is it's converging because of the cancellation. Okay, if you look back to our first example, The reason it converged was it kept popping back and forth. Okay, so there was a lot of canceling going on between the positive and negative terms. As a matter of fact, if you actually were to add up all the positive terms or to add up all the negative terms, those would diverge. So it's basically an infinity minus infinity case. That creates some weird things. I'll let you read through the book for that one. We're not going to do too much with it. The main thing to realize is when you have something that converges conditionally, you really got to be careful doing the algebra with it. Because if you regroup the terms in some way, you actually can end up changing the value of the sum. That's sort of a weird thing. We're so used to addition being associative, but this is an infinite sum. So for finite things, that works fine. But in these infinite sums, weird things can happen when you have a conditionally convergent sum. So when you go on the future courses, real analysis and so on, we're going to be interested in, okay, when is it absolute convergence? When it's absolutely convergent, you can do all the algebra you want. It's not going to have any effect on the value. Conditionally convergent ones are a little funny. So for now, we're just worried about the definition, but you will see these again later, especially like in real analysis and some differential equations. Okay, let's take one example here just to show how this would work. Let's look at the sum. And this is actually stolen from the book, so it's number 25 if you're curious. -1 to the n plus 1, and then we have n plus 1 over n squared. Okay, and that's from n equals 1 to infinity. Notice we start with n plus 1. That means we're starting with the positive term. So when we plugged in 1, we'd get 1 plus 1 over, okay, so that's going to be 2. We plug in 2, we're going to get 3 over 4. Go plug in 3, you get 3 plus 1 is 4 over 9. 5 over 16 plus 6 over 25, and so on. Okay, it's often helpful, especially with these alternating ones, to write out the first 3 or 4 terms just to get an idea of what this thing is doing. Okay, well, it's alternating. The size of these things, I'm going from a 2 to a 3/4 to a 4/9 to a 5/16 to a 6/25. Most certainly, the size is shrinking. And that's because you have an n squared in the denominator and n in the numerator. So it fits the description for the alternating series test. So it converges by alternating series. Now, the alternating series test in and of itself won't tell you whether that convergence is conditional or absolute. One thing you'll want to note in the homework is in the first batch of questions, they're just asking you to use alternating series test. It's only in the questions past 15 that they're asking you to check for absolute convergence. Okay, so you'll have 3 possibilities once you reach number 15. That'd be converge absolutely, converge conditionally, or diverge. Okay, so we got to determine whether or not this is absolute convergence. Well, if we got rid of that -1, notice this is a different series. We're just asking, well, does it work if you don't have that -1? Well, n plus 1 over n squared most certainly is larger than n over n squared, which is 1 over n. And we know the sum n equals 1 to infinity of 1 over n diverges. Okay, that's our rule for P series. Well, that means a bigger one is an also diverge. So by direct comparison, 1 in there. Yeah, let me put it afterward. It's going to converge conditionally. Because if I look at this one, it's bigger than something that diverges, so most likely this one diverges. So this alternating series says it converges, but it has to be conditional because it's not absolute. Okay, so it's a little bit tricky in terms of the terminology in this section. However, the actual algebra isn't all that bad. You simply check, are the terms going to 0? Are they shrinking? Then the alternating series test will tell you automatically. Now, sometimes you don't want to get too fancy if you don't have to. So let's take one that's a little more straightforward here. So let's say I had something like the sum n equals 1 to infinity of negative negative 1 to the n times 3/4 to the n. Well, this does fit the description for the alternating series test, but it's geometric. Okay, so don't forget your other tests out there. If it's geometric, like this one is, you might as well just say that r is negative 3/4, so it converges. And geometric series, because they are between -1 and 1, they actually converge absolutely when they converge. So if you see one of the other tests that would apply, go ahead and use it. Don't feel that you have to use alternating series test. It's just one more tool. So we always want to pick whatever tool we think is going to work the best. Okay, well, we only have really 1.5 sections, really. The next 2 sections belong together. And that is dealing with, can we write a function in terms of a series? So what about the sum n equals 0 to infinity of x to the n? Now that's geometric. That's going to be 1 plus x squared, x cubed, and so on. The question is, does it converge as a function? Well, since it's geometric, it's going to converge whenever this value you're taking a power of is between -1 and 1, so it converges Okay, so the next 2 sections really deal with this. The first one says, well, if we're given the series here, what is the domain for that function? The second section, which is going to be our last section for the semester, asks, okay, if I'm given the function, how do I find this series? And that's called Taylor's theorem. It's a very important theorem in math, and it's a good place for us to close the semester out. So look for that to be coming out, and hope all is well with you and stay healthy. And we'll be catching up with you in the next day or 2.